the second derivative test. And we're going to learn what the second derivative test can tell you about the graph of a function. Okay? And we're learning to use a second derivative test to find points of inflection.
Are we recording right now?
And
Where's the recording?
where we're concave up or concave down. With 21 seconds in card.
Sorry.
Right?
Calculus is the best.
What does the second derivative tell us about the graph of a function? Okay. So I'm doing really basic functions here so everyone can catch on. Okay? So if I draw my x and y axis in here, and could I call this y equals negative x squared, that function, and you'd be okay with it?
Yeah.
Okay. So y prime would be negative 2x, agreed?
Yeah.
And what does y prime mean? It means the slope of the tangent, right? So for instance, if I wanted the slope of the tangent, remember this means slope of tangent. Say I want the slope of the tangent at -1. I would stuff -1 in here. And that would give me +2, which means when x is -1, the slope of my tangent would be +2. Does that make sense? Okay, so right here my tangent would have a slope of +2-ish. Okay? What happens for y prime at 0? 0, which means I should have a horizontal tangent, right? And then how about y prime at +1? -2. So, okay. So that's what the first derivative tells me, and that's what we know about the first derivative. Now, the second derivative means you take the first derivative and you derive it, and we call it y double prime. Okay? Y double prime.
Sneaky prime.
So what happens when you take the derivative of the derivative?
You get a derivative double slope.
What would you get in this case? -2. That shows that over the entire interval for y equals -x squared, the slopes of the tangents are decreasing the whole time. Okay, so you can see, I'm sorry, the slopes of the tangents are decreasing, yeah. So we go from positive tangents to negative tangents over that interval. Okay, so they're getting smaller and smaller and smaller, so we're at a strong positive, less strong positive, less strong positive to 0, and then we're to a negative to a very steep negative. So over that whole interval, our slopes of our tangents are decreasing. Okay? This means, so whenever you get a y double prime to be negative, it's said that we are concave down. And concave down means when you draw your graph, it's going to look like a frown. Okay? So it gives you a better idea of how to draw the curves. Okay, so over that whole interval, we're concave down. Yep.
What does like the 2 have to do with it?
The -2?
Yeah, what does the 2 mean? Like what does it do to them?
All we care about is the sign. Okay, so if it's negative, we're concave down. If this turned out to be positive, we'd be concave up. Okay, and I'm using the most basic example so that when we get to the more complicated one, you understand.
Sorry, it sounds like Andrew asked a stupid question.
No, it was a good question. All right, so, and this says if the first derivative is 0 and the derivative is decreasing, so negative, okay, is negative. That's another way of saying is negative here, right? And what's this notation? That's weird, right?
dy over dx.
Yeah, so when you have dy over dx, which means the slope of the tangent, but you want the second derivative, it's the second derivative of y with respect to x twice, okay? Because you're taking the derivative of y with respect to x once, and then you're taking the derivative of that with respect to x again. Okay, so this 2 is between, it's an exponent, or it looks like an exponent between the 2 and the y. Okay, this means y double prime. Okay, it means f double prime of x. Okay, it's just a Leibniz way of writing it. Okay. So if the first derivative is 0 and the second derivative is negative, then your critical point is a maximum. So let's just look at that again. Does it make sense that our first derivative would be 0 right there? Yes, and our second derivative is negative, and this is in fact a maximum. Okay? All right, so, and this is, all right, so we were starting off here. So again, I'm going to do the same thing here, put this on an axis, and we're going to call it y equals x squared, positive x squared this time. So y prime is 2x. So whenever I put a negative in there, the negative number, I'm going to have a negative tangent, or negative slope of tangent. Everyone agree? These are all negative. When I put 0 in, horizontal tangent, right here. And when I put a positive number in, I get a positive slope. So that's what the first derivative tells me. Okay, we're used to that. Now if I find y double prime, it's positive this time, which means the slope of the tangent is increasing the whole time. Okay, so we go from a very steep negative number, like say negative 2,000, and then we're getting bigger because we're getting to like negative 1 and negative 0.5, all the way to 0, and then we're increasing after that. Okay, so the slopes of the tangents are always increasing, which means we're concave up, which is a smile, over this whole interval, concave up. Okay? And then that's, again, summarizing if y prime is equal to 0, and the derivative is increasing, which means positive, which means y double prime is greater than 0, then your critical point is a minimum, which is what we have right here, a minimum. So you might be saying, okay, it's showing me how to draw the picture, that's nice, but I already know how to find a maximum and a minimum from the first derivative test. What else can the second derivative test tell me? And it's coming up. Here we go.
Yeah.
All right, so here's a case where here's our critical number. Our slope of our tangent is 0, right? So y prime is 0 at this point. But it's not a maximum or a minimum, is it? But we're concave up here because we draw our tangents underneath. So this side is concave up. Smile. Everyone good? And then this part is concave down. Frown. And this is the point where you change from being concave up to concave down. And that special point is called a point of inflection, or an inflection point. And that's where you change from being concave up to being concave down.
Okay. Yeah.
Or that means point of intersection.
Point of inflection, don't see abbreviation, nothing.
POIN, I guess. So you have a point of inflection if you go from concave up to concave down, or if you go from concave down to concave up, that would also be a point of inflection. Okay? So that's another thing the second derivative test tells us. That's actually what the second derivative test is for, to find out where points of inflection are. Okay, we use first derivative test for maximums and minimums. We use second derivative test to find where our points of inflection are. Now we've got even more info to draw our graphs. Okay? All right, so here's our first question. So we're going to use the first derivative test and the second derivative test to determine any local maximum and minimum values of the function. I should say, and any points of inflection. And there's room on the next page.
Wow, the water.
Well, we get to the first derivative test, the second derivative test, and draw pictures. So I'm going to pause. All right, I'm going to catch up to you guys.
Not on my watch.
We'll see about that.
Uh-oh, is that a challenge? I'm getting nervous now. Oh, my watch. Holy, this is getting nice. Dominant right now. Okay. You already got it wrong, bro. No, I didn't. What is it wrong? What is it read? Look at. No. No, it is 3. Shit. It's alright, it's just a minor blip. It's just a minor blip. Okay. 0, funny 0. What is the page? I'm just trying to refresh here. Oh, that's a huge number. Oh, what am I doing? Yo, where's my eraser? No, you're up. Shit. It's not good. It's not good. Okay, bro, what is this? You're wrong here. Oh, what is it? What did you guys get? Yeah, it's 48. What grade do you play everything? The top one is the top one.
57?
Yeah, I got that.
You did? Great. Awesome. Okay. Is it right though?
Yeah, I put it in.
Yes. Okay, good. You're good? All right, so now, before we do any sketching, now we're going to do the second derivative test. So we bring down the first derivative. Bring down the first derivative.
Why are you hitting me?
F prime at x equals, oh, and we don't want this one, we want the original one. We want, because it's easier to derive, we don't have to use a product. So we want the f prime at x, oops, is negative 12x squared plus 36x. Okay, so now we want to find f double prime at x.
Alright.
F prime at x. So taking the derivative of the derivative, what's that going to give me? Negative 24x plus 36.
So
Awesome.
negatives.
Then I'm going to try to put it into factored form. So what's common between negative 24x and 36?
6.
Negative 12?
12.
So if I divide negative 24x by negative 12, I get 2x.
Yeah.
And if I divide 36 by negative 12, negative 3. And then I want to see where is the second derivative 0. Okay, where is it 0? Because that's where we have a point of inflection, where the second derivative is 0. Okay? So negative 12 is not going to give me anything. When could this factor be equal to 0? 3/2 is good, and I'll just show you how to get that if you're not sure. So to do like a little grade 9 equation, you want to know when is this equal to 0. So you put equal to 0, add 3 to both sides, divide both sides by 2, and you get x equals 3/2, like Jacob said. So then we don't call this a critical value, we call it a possible point of inflection.
Why is it possible?
Because the rational functions are not always points of inflection. The polynomial they are, but it's not the right words, just in case. You never know.
You know why it
Because
is?
loves curve sketching so much he does it. I don't know. So possible point of inflection at x equals 3/2, and then we're doing the second derivative test, s dt, second derivative test on f double prime at x equals negative 12 times 2x minus 3. We've only got one possible point of inflection, so it should be really easy to make up our interval chart,
We
right?
just add the.
So there's only one here, right, at 3/2. So we've got negative infinity to 3/2. X equals 3/2. And 3/2 to infinity would be our intervals. Okay? And then our chart is very similar to what it was with the first derivative test. So we want the sine of the second derivative. So sine of f double prime at x, a picture, and a conclusion. So we always want to pick easy points. So an easy number between negative infinity and 1.5 would be 0. Does everyone agree with that? So this negative 12 is going to stay negative, and this is going to be negative because it's going to be 0 minus 3. So overall it's positive, and in this case that means concave up. Here's my picture, a smile. Okay? And my conclusion is concave up. Okay? So my picture is a smile, my conclusion is concave up. At x equals 3/2, we're neutral. Okay, that was our 0. And I don't know whether it's going to be a point of inflection until I go over here, so I'm not going to draw a little point in there until I know if it is a point of inflection. Okay. Then over here, so I'm going to use 1, so I'm going to use 2. So that's still going to be negative. 2 times 2 is 4, minus 3 is 1, so it's positive. So overall it's negative. Brown, concave down, which means this is a point of inflection. At 3/2, which is harder to sub in, and usually that's the hardest part of these questions, is subbing in fractions and roots and stuff, but it's not that hard when you have as much time as you want to work it out. So we need to find f at 3/2. Okay, so you gotta remember a few things. So when you cube a fraction, you cube the top and cube the bottom. So 3 cubed is 27 and 2 cubed is 8. Okay? Plus 18 times 9 over 4 plus 3. We go over here. So negative 4 times 27 is negative 108 over 8 plus 162 over 4 plus 3, common denominator of 8. Just have to multiply 162 by 2.
Yep.
So that's going to be 108 plus 324 plus 24, 456 over 8. And Carter says that goes in evenly. 57?
Okay.
You got 30?
Yeah, I got it wrong.
Who else got 30?
I put my calculator.
You got 32, Sam? You got 30? Okay, we're like, oh, negative 108. Thanks. Thank you. Way to go, guys.
Negative or something.
Yeah, it is sneaky. Negative 108 plus 324 plus 24. 240 divided by 8. That is 30.
You hear that recording? I was part of this
Yes,
one.
yes, you beat the teacher. All right, so now we go back down here, all the way to our chart.
Yeah, what here?
And now we put all our info together to draw a sketch. Woo.
Right. Is it okay that I got that number didn't show before?
Is it okay if you didn't show any work?
I just put it in my calculator.
Oh, you mean for the calculation? Yes.
That's alright?
Yes.
Okay.
But I thought you meant the whole thing.
No, it's like that
Read the
part.
graph. Okay, so we want to go as high as 57 and as low as 3. And what's our y-intercept? 3. Okay, so I'm going to put my x-axis near the bottom. So here's 0, 3. We have 3 and 57, so I'm going to put that over here. And then 1.5, so that's halfway between here and here. That's 3 over 2. You know what's cool about 30? It's halfway between 3 and 57. Because 53 to 57 is how much? 54. Yes. So,
Yes.
yes, so it's 27 to each one, which is halfway between. Which is cool. So we pick a part that looks halfway. And that's our 3 over 2, 30. Okay? Won't always happen, but sometimes does. And then we want to look at our second derivative test. It says I'm going to be concave up from negative infinity to 3 over 2. Concave up is a smiley face, right?
Yeah.
So I'm always going to be concave up. So here I go, concave up from here to here. Big smiley face, and I can put an arrow this way. And then my second derivative test says I'm always concave down from 3 over 2 to infinity.
Can you draw the dot for something?
Sorry?
Can you draw a dot for something?
Dot with a smiley face?
Look at eyes.
Oh,
Is that alright?
I guess so. I haven't even asked me that before.
That's the worst. I don't know what that means, Kevin.
Okay, so if you see here, here's our tangents underneath, right? Here's our point of inflection, and now here's our tangents on top. Okay, so we switch from concave up to concave down. Okay? Yeah? Okay, great. Oh wait, did I miss something? Okay, so this just highlights again that a point of inflection is a point at which a curve changes concavity. Okay? That concave up represents a positive second derivative, concave down represents a negative second derivative, and a point of inflection can only occur at places where the second derivative is 0. That's the only place you can change from concave up to concave down. Okay? And then this just outlines a second derivative test, but we just did it, so I think you know how to do it. This is just in math terms. Next example. All right, so you guys do the first. Is everybody okay here?
Oh, yeah.
So you can have a common factor, difference of squares, and then that difference of squares can be factored. Now you set it equal to 0. And now you get your critical values. So -1, I like to put them in order from smallest to biggest. And now I'm going to do the first derivative test on y prime equals 4x times x minus 1 times x plus 1. Six. Okay, so again, once you find your, that you have a local min, you have to take your x value, set it into the original equation to get the corresponding y value for your function. Okay? Okay, positive 0.5 here, so that means that's your positive, still negative, so negative overall, decreasing, which means we have a local max at 0, and something 0 you can do in your head, 0, 7, x equals 1, horizontal tangent again. I'm gonna get 2, which makes everything positive. So we're increasing. So we have a local min at 1. And this is still gonna be the same, right? 6?
Carter Galloping if needed.
Okay, so thank you, Mr. Rudy. Oh, you go. Oh! Oh, you can hole punch them. Nice. Okay, first derivative class, any questions? Pretty good for that? All right, so now we're moving on to the second derivative. So we're going to take our first derivative. Y prime prime. So y prime prime is 12x squared minus 4. Agreed? Now I want to put it in factored form. Is there anything I can factor out of there? 4? But that's not a difference of squares, is it? At least not a pretty one. All right, so we have to use something else. This is where I said that the messy numbers come in, but that's the only hard difference. Okay? So we know that to solve this equation, 4 is never going to become 0. It's a constant. So the only way this equation can be true if there's some number or numbers that make 3x squared minus 1 equal to 0. Does everyone agree with that? So I'm going to make myself a little mini equation, but this is a mini grade 10 equation instead of a mini grade 9 equation. How do I get x by itself? What do I do first? Add 1 to both sides?
Square.
Not yet. Divide by 3. Square root, and what's special about quadratic equations? How many solutions do they usually have? 2 plus or minus. Okay, so I'm solving that kind of mini grade 10 equation there. So I get x equals, now do you guys agree that I can do this positive or negative root of 1 over root of 3? Okay, and what do we know about the root of 1? It's 1. So positive or negative 1 over root 3. So therefore, the possible points of inflection occur at x equals negative 1 over root 3 or 1 over root 3. Those are where my possible points of inflection are. Okay. So now I want to do my second derivative test on y double prime equals 4 times 3x squared minus 1. Okay? So with 2 possible points of inflection, I'm going to have 3 intervals, right? You got what? Negative infinity to negative 1 over root 3. X equals negative 1 over root 3. Negative 1 over root 3 to positive 1 over root 3. X equals 1 over root 3. And then 1 over root 3 to infinity. Those are back. You can go into the back, can't you?
No, good question.
What about the very back?
No. No.
Yeah. Answer stuff.
Yeah, underneath the answers.
Okay.
So you can move to underneath the answers if you run out of room.
Make it work.
Okay, so here we're looking at the sign of y double prime, a little picture, and a conclusion. will be the last example we do. We'll finish tomorrow. Okay, so we need a representative number between negative infinity and negative 1 over root 3. So we probably want to know what negative 1 over root 3 is, right? Approximately. It's not an issue. So negative 1 divided by the square root of 3 is approximately negative 0.577, like approximately negative 0.6. So what could I choose and be in that interval? An easy number to choose. Negative 1. So I'm going to choose negative 1. So this is going to be positive. And this is going to be positive. Because I'd have negative 1 squared is 1 times 3. 3 minus 1 is 2. Pretty good? So positive doesn't mean increasing here. It means concave up. Okay? Concave up. X equals negative 1 over root 3 is where I'm 0. But I don't know if it's a point of inflection yet, so I'm going to come between here. So this is between negative 0.6 and positive 0.6-ish, right? 0 is a perfect one to choose, right? So that's going to make this one negative now, because I'm going to have 0 minus 1. So I'm going to be concave down, which means I've got a point of inflection. Okay, so here's where the hardest part of the question is. So I'm going to go through it nice and slowly. And then something really nice happens later. So I have to do it. Okay, so I'm writing out my original equation, which was y equals x to the 4th minus 2x squared plus 7. Carter's going to do it all on his calculator, but we're not all that lucky. So we have to sub in 1 over root 3 to the 4th minus 2 times 1 over root 3 squared plus 7.
Can you change it to decimal?
Sorry, and it's negative, isn't it? Negative. No, you can't change 2 decimal. You want perfect answers. Perfect. Calculus is pretty imperfect. Okay. Now, when you have a fraction to an exponent, you can apply it to the top and the bottom. Pretty good? So when you put negative 1 to the power 4, what are you going to get? Positive 1. Okay, so when you square root 3, what do you get? 3. And then if you square twice, are you really putting it to the power 4? So this bottom is 9. Try on your calculator root 3 to the power 4 and make sure you get 9, so you know how to do it on your calculator as well. Okay? So make sure you can do root 3 to the power 4 and get 9. 9? Oops. Eraser. Okay, so now we're minus 2. Oops. Okay, minus 2 times, so if I square negative 1, I get 1. If I square root of 3, I get 3. So y is 1/9 minus 2/3, because this is really over 1 here, plus 7. And now I need a common denominator of 9. So 3 times 3, 2 times 3. So 1 minus 6 plus 63 is 58 over 9. So then my point of inflection is at negative 1 over root 3, 58 over 9. Okay? All right, so here we know that when we put positive 1 over 3, we're going to get 0. Here I'm going to choose, this is 0.6, I'm going to choose 1 for that interval. So positive times positive is positive, so I'm going to be concave up. So this is another point of inflection. at positive 1 over root 3. So who can tell me what the fortunate thing that happened because the function is this? Right. So both of the exponents are even numbers, so does it matter whether I put negative 1 over root 3 or positive 1 over root 3 in? No, because I'm going to end up with positive. Okay, so I don't have to do this whole calculation again. I know it's going to be exactly the same as it was here, which is 58 over 9. Okay? So that saves me from doing it twice, which is nice. All right, now we want to put our information together in a sketch. So we go back to our first chart here. We want negative 1, 6, 0, 7, and 1, 6. So negative 1, 6, 0, 7. Positive, oops, lower down. Positive 1, 6. And then I've got to add in these guys. So we have to know what they approximately are. So we said this is like approximately negative 0.6. 58 over 9 is about 6.4. And this is going to be positive 0.6 and about 6.4. So negative 0.6 is just a tiny bit closer to negative 1 than 0. Is everybody good? And 6.4 is, so these are just 1 between them, so it's a little bit closer to 6. So like here. And then it's going to be exactly symmetrical on this side. And those points then I should write in are, well, this one's 1 over root 3, 58 over 9. And this one's negative 1 over root 3, 58 over 9. So now I want to draw my curve. So it says I'm concave up from negative infinity to negative 1 over root 3. So concave up from here on, okay? This is an inflection point, so I'm going to change to concave down between negative 1 over root 3 and positive 1 over root 3. So I'm just going to do this in a different color. Purple. Oh, that was hard. Undo. I'll do the purple better later. Okay, so that's my purple part. It's concave down. And then I'm concave up again from 1 over root 3 to infinity. So there's, it should look more nicer, but get it? Okay, so we're going to stop there. I know it was